Yes.
Yes, I believe I can hear you clearly.
Okay. We wait our fearless leader, Marie-José, but I am not seeing her on the participant list. So I think I will welcome you myself. Welcome everyone to the COINRG session. Welcome to our speakers, welcome to those of you who regularly attend, and welcome to our new attendees. I'm Eve Schuler, and I have two co-chairs, Jeffrey and Marie-José, and we sometimes refer to ourselves as GEM. You're at the IETF 110, and we're virtually in Prague. The documentation and materials for this session can be found online through the data tracker. Remember that all of these sessions are being recorded, and please ensure that your video's off. Keep yourself muted, and we will monitor the chat cues for you, the chat as well as the queue for speaking. In case you have not attended the IETF and IRTF before, and in fact, COINRG is part of the IRTF, there are intellectual property rights disclosure rules that are crisply described in many documents. And by participating in the IRTF, you agree to many of these processes and policies implicitly by joining the session.
Hello, everyone. I'm sorry. I'm sorry. I had connectivity issues. So
terrific. Let me just get through this, and then
yeah.
I will advance for you. And then when we get to the presentations, then I'll switch over and I'll do note taking, and you can continue. Additionally, the privacy and code of conduct, there are high standards documented in these places. And the goals of the IRTF are slightly different than the IETF. They're to conduct research. It's not about standards development, although there is certainly precedent for groups in the IRTF to mature into groups into the IETF, but that is not our intent. It is really to be a forum and community for research. Marie-José,
yes, and actually I would like to point on the last slide. I know we're going to have a number of presentations today by new people in the group, and I think it's very important to highlight what is related to a research community in your presentations. And we're not a working group, and we're not going to produce any standards. So we can go to the next slide. You're sharing, Eve. You want me? Well, let's wait.
We'll switch over when the presentation.
Yeah, we'll switch over. So our goal, essentially, because we're a research group, we would like to create a dynamic community for computing in the network and on the network, because I think we've made progress in both directions, and to share and define the research that will help to use computing to improve performance in networks, in applications, and eventually to users. So it's not about, again, it's not about creating standards to implement in industry. It's about to create that research community that eventually will evolve most likely into industry projects and technology transfers. So the scope obviously is the evolution of these systems, the architectures. You're going to see a lot of that today, the protocols that are being used and how they can also evolve within the research community, and real world use cases, application, and obviously a lot of work in progress. The focus is the core edge compute continuum and the constant melding that's happening right now between networking and computing and storage, because obviously the act of storing is also a form of computing. Next slide. So today's presentations, we continued the trend that we started at the last IETF a little bit, but mostly at the interim, which is having invited papers that are relevant to the evolution of COIN. So today we have all these papers, and they cover architectures, computing and distributed systems. I would say data set more than databases, storage and edge devices. Obviously, the whole move to distributed information systems across the network. Deployment aspects, and also we're going to have a short draft update. There's a lot of research going on. We have a few drafts that have expired and that will need some attention from the authors, but we're going to talk about that after the presentations. So a short summary of the research. The slides are available, so that's why there's links to the papers there. So if you're going to have obviously the slides in the data tracker, but you can also get the papers. So we're going to have first a presentation, the flow lens, which was presented at NDSS. We're going to have a review of some of the work from Theo at Stanford, and he also works with Robert Soule at Yale, who is one of the, I would say, leading researchers in computing in the network. We're going to have presentation from Georgia Tech on distributed data storage. Another presentation from Toronto on session consistency, and the project from Ericsson on connected intelligent machines that actually requires a lot of processing. And then we're going to have an update on the COIN app, the network computing for app-centric microservices from Dirk Drawson, and two presentations from Hemant Singh. You may probably not have seen his name a lot. He was very, very active when we did the hackathon, and he's a leading researcher in P4. So he's going to present that. I see there's a typo, but that's fine. And then we hope to have time for discussions and see a little bit, how we can evolve a few things. And then we are going to go through some conclusions and future plans, and especially the goals for the next meetings and the interim. So this is it. I don't want to take more time. We want to go directly into the presentations, and should.
Why don't you grab the screen and you can.
Yes, I will grab the screen and share for the presentation.
I'm not entirely sure how to.
Well, I'm actually sharing. I'm actually requesting to share my screen. I think you have to stop sharing yours.
Oh, I see it. I see it. I was just trying to find that little widget that likes to go away. There you go.
Okay, so then I can share
all
mine.
Yours. And I would like to tell people that I am taking notes, which if you go to the top of the Meet Echo screen is the button that has the pencil over the paper, and that takes you right to CodeMD. And please, it's a group sharing note-taking tool. So by all means, if you have some comments you want to make, we'll be monitoring the chat as well. But feel free to add your notes into the meeting notes through
do you see my,
and through
do you see my slide? Do you see my screen now?
No.
Oh, I'm supposed to be sharing my screen. Well, it says that it doesn't want to share my screen. Nice. Diogo, can you try to share yours?
Yeah, sure. So I would actually propose that. So let me try.
And if that doesn't work, I'm happy to share again. It's just hard to note take and share screen at the same time.
So it says that I'm in this sort of queue.
Yes, there, I see you.
Okay.
There you go.
Great. Thank you.
Thank you. Let me just check if I can. Okay, so I'm gonna share my entire screen, I guess. Can you see my slides now?
Yes, perfect.
Okay,
So
Okay, so
all
I guess I can start
presenters,
now.
because of my issues this morning, with Teams, all presenters, please share from your own computers. So go ahead, Diogo.
Okay, so thank you so much for having me presenting my work here at the COINRG. So my work is joint work with Nuno Santos, Luís Rodrigues, Fernando Ramos, and André Madeira from INESCIDE, Instituto Superior Técnico, University of Lisbon, and also Salvatore Signorello from LASIS, Faculdade de Ciências, University of Lisbon as well. And so today I'm going to talk a little bit about our system called FlowLens that used programmable switches to enable a range of machine learning-based security applications in the network. So as of today, we know that there have been a number of performance breakthroughs with programmable switches, and these devices are able to process packets at terabit per second speeds, at line speed, can be fully programmable in the P4 language, and have also been the recent focus of different hardware manufacturers. And so they actually bring new opportunities in the realm of network security. And as a matter of fact, these switches have also been used by different authors to propose new security applications in the network, such as the obfuscation of network topologies, the filtering of spoofed IP traffic, mitigation of DDoS attacks, or also to thwart network cover channels. And by using programmable switching devices, all these tasks can actually be made highly efficient and process packets at line speed. But however, as you can see, they are actually fine-tuned for a very specific application domains. And unfortunately, they ignore some other important applications that depend on machine learning. And so within these applications, we can think of the detection of botnet traffic, the fingerprinting of websites, that is identifying a website that is being browsed by a given client over an encrypted circuit. Also to perform the analysis of the behavior of different IoT devices, like smart home devices, and also to detect cover channels. So one thing that all these applications have in common is that they rely on some kind of statistical traffic analysis that analyzes and extracts features from the distributions of packet lengths or inter-arrival times of such network flows, and then use a machine learning-based classifier to distinguish between different classes of traffic, let's say malicious traffic from benign traffic within an organization. And as you can see as well, so this is some sort of a generic approach to detect multiple attacks. However, collecting these packet distributions in programmable switches is actually a hard task. So on the one hand, we know that the stateful memory that is available in these kind of devices is very limited and typically just allows for keeping track of a few hundreds of megabytes of SRAM. And this just has no memory for storing many flows that can cross these switches concurrently. Not all that, we know also that packets must be processed at line speed within these devices, which typically means processing packets within the switches under a few tens of nanoseconds. And we can only use a limited number of operations to do this, also using a reduced and often domain-specific instruction set. And so this actually raises the question that it really doesn't seem feasible to obtain these packet distributions in programmable switches at scale to enable these machine learning-based applications. So in our research, we tackled this question of whether we could collect these packet distributions within programmable switches, but such that we could do that efficiently and also to support generic machine learning-based classifiers. So we know that there are being proposed different solutions for collecting these packet distributions, also with the aid of programmable switches. So for instance, Starflow proposes this kind of packet duplication approach back to a monitoring server. And while this approach is generic, it incurs in a large bandwidth costs by sending these packet properties back to this monitoring server. And we also have other approaches such as NetWarden, which can actually perform some kind of computation on the packet distributions of flows within the programmable switch itself, but can only
Not hear you.
Audio of our speaker. Diogo, are you hearing us? Did you type in the chat window?
Diogo, do you hear us? We don't hear you anymore.
We still see your slides. We don't hear you.
Yeah, he thinks he's still, I don't know how to send him a message.
Maybe a private message.
Well, that's not helping.
Maybe we can alert him by taking away the screen, and then he won't see anything. And
Well, I did
oh,
that.
okay. Let's see if he hears this.
Diogo, if you hear us, you lost the sound. So I revoked the screen so that you can maybe start resharing and maybe the sound will get back.
Sometimes when you use the arrow key all the way at the bottom of the screen, the far right, there's two arrows, and it suggests to reconnect the audio. Sometimes that will help, if you could try that. But I'm suspecting he can't hear us, so I'm going to type him that as well.
Okay, so while we figure this, I'll send him an email. While we figure this out, is the other presenter available? The next presenter, Theo?
I'm here.
Okay, so yeah, let's start. Let's do you and let's switch around because I have the impression there's a problem. I'm going to send Diogo an email, but please do your presentation and we'll come back to Diogo.
Okay, I asked us to share my screen.
Yes, we have given you
Can I
permission.
choose? Okay. Can you see this?
We can.
Okay.
It says forwarding with software middleware.
Yeah. Okay. So, okay.
Yeah. You probably want to go to the beginning. Yeah. Perfect. Thank you.
And I remind everyone that you have 15 minutes. So, but I'm dealing with the Diogo right now.
Okay.
Go ahead,
Okay.
Theo.
Okay. So I'm going to tell you why networks should and can provide more expressive routing. And this is a little bit controversial because it touches on the end-to-end principle, but I think you'll enjoy it. So I worked on this together with Ali Fazoliman, Masoud Moshref, Antonio Carceniga, Nate Foster, and Robert Soy. This was done at when I was interning at Barefoot Networks and at Università della Svizzera Italiana. But now I'm at Stanford University. So what is the interface that the network provides? It lets hosts send packets, and these packets must have the IP address of the destination. The IP address specifies where, the location in the network that the packet must be forwarded to. But is this the abstraction that applications use? Most applications have no inherent notion of IP addresses. So we see a fundamental mismatch between the application requirements and the API provided by the network. So how do applications actually communicate. Let's look at some modes of communication. In a microservice environment, services don't send requests to the physical host, but to a service by ID. With load balancer, applications don't contact a specific server, but the server with the lowest load. And in publish-subscribe systems, like Apache Kafka or ActiveMQ, they let applications send messages to topics and the middleware, or the software broker, forwards the messages to their destinations. So these systems provide more expressive routing than just IP forwarding, but they're slow. Compared to network devices, they introduce significant latency and can't handle the same throughputs. Let's see an example. Let's say we have a publisher that sends messages with different attributes or fields. For example, a message with a topic art that has received 70 likes so far. Then there are services like analytics services, which want to receive some of these messages. One is only interested in art, another only in sports. One would like art with more than 50 likes. How can we do this today? The publisher first sends a message to the software middleware, like Kafka, which brokers the message. It figures out who should receive the message and sends it to each destination. This is not ideal. Not only do packets not take the most direct path, but they also rely on the middleware, running in software which is slow, introducing latency, and can't scale to high throughputs. Furthermore, there's extra traffic, because the middleware has to send a separate packet to each host, and it can't take advantage of multicast. We think that the network itself should do the filtering and routing based on the content of the messages. The idea of predicate forwarding is not new. There have been many proponents of this information-centric networking, or ICN. We argue that now there's also a performance benefit of this expressive routing, and it's time to revisit these ideas in a controlled environment, leveraging emerging hardware trends. We now have programmable devices in the network that are not tied down to traditional routing. We propose packet subscriptions, a new way to think about routing in the network in application-oriented terms, which can be implemented efficiently. So what do packet subscriptions look like? A packet subscription lets an application decide how the network should process a packet based on its content. In its simplest form, a subscription identifies a packet and executes an action. For example, if the topic of the message is art, forward it to host 1. Subscriptions can also be more complex. For example, we can filter messages for sports that have more than 70 likes. And if multiple hosts want the same packet, we can do multicast. This is a powerful abstraction because it decouples the locations from addresses from the content of the messages. But how do we make this practical? It's not so straightforward to get this working. At the switch local level, how do we run these rules? We need to compile them somehow and execute them efficiently at line rate. And then, from the global perspective, how do we route with rules in the network? Which switches should store the rules? I'll show you how we tackled both of these challenges. But let's start looking at the single switch. As inputs, we have an application specification, which indicates the type of packets we'll be processing. And we have subscriptions from the hosts. The application specification, which doesn't change often, is compiled once to generate a pipeline of tables on the switch. Each of these tables checks a different field. For example, one table will check the topic field, another the field with the number of likes. And then at runtime, we can populate these tables with compiled subscriptions. So a naive approach would use too many resources to fit in the switch. It would create too many table entries that just wouldn't fit. So let's take a look at how we can populate these tables efficiently. Here are some rules for filtering messages. How do we represent these rules in a compact way? We chose to convert them into a binary decision diagram, a BDD. This data structure has some useful properties like storing overlapping subscriptions. This tree-like structure essentially encodes the logic of matching a packet. You can think of it as a finite state machine. We traverse the tree from top to bottom starting at the root node. And each node predicates on a field in the packet. If the predicate is true, you take the true solid line. Otherwise, the dotted line if it's false. And finally, you arrive at the leaf node at the bottom. This indicates the action to be taken. But how do we execute this data structure on the switch? This is one of our key contributions. We have to convert the BDD into tables. We do this by slicing the tree, grouping predicates on the same field. For example, these are the predicates for the likes field. And each slice is used to populate a different table. Essentially, these tables encode a finite state machine. Each table matches on one of the predicates and updates a state variable that corresponds to our location in the tree. This state is passed from table to table, and at the last table, depending on the current state, it executes the appropriate action, like forward to a host or drop the packet. So I showed you how we compiled the rules for a single switch. The second challenge is routing with these rules. And it's not as simple as you may think. There are a number of different ways in which we could route the packets, and there are trade-offs of choosing one particular scheme. I'll show you two schemes in detail. Let's say a subscriber only wants messages with topic art. Which switches should store this rule? Well, all the switches going up the topology must store this rule. And for each of these switches, we calculate the shortest path and forward the packet down the appropriate link. But how about the other side of the network? How about going up the topology from a sender on the other side? Do we need to store all the rules on the other side? In the first routing scheme, we want to reduce extra traffic in the network. So on the other side, going up, we send all the matching packets up the topology. And this requires storing the rule on all of the switches. So every switch in the network needs to store every single rule. And this uses a lot of memory. But it doesn't send any extra traffic because it sends each packet on the most direct, efficient path. Alternatively, we can use a memory reduction scheme if we want to store less rules. Instead of matching on the topic art, going up the topology, we forward all the packets that arrive from below upwards until the core switch. Then the core switch forwards the packets down. So the core switch needs to store all of the rules. So this uses less memory than the other scheme, but it comes at the expense of sending more traffic because all packets have to go all the way up to the top of the topology before they can start going down. So you should see our paper for another scheme that does approximation through parameter space discretization. This reduces the number of rules and also saves bandwidth. In our evaluation, I'll show you how the schemes I showed you here compare. So we built a prototype of packet subscriptions, and we use it to answer several questions. Our first question is, are packet subscriptions useful to applications? Does it provide the interface that they need? To answer this, we implemented several applications. We use packet subscriptions to filter the NASDAQ itch feed, and we routed video streams for Cisco's hybrid ICN system. And we used it to detect network events and streams of in-band network telemetry, INT data. The market filtering and the network telemetry applications did not require any changes to use packet subscriptions. We could use the packet header formats from the original protocols. And this demonstrates that packet subscriptions provide the right interface for these applications. The second question we had is, does packet subscriptions provide performance benefits? Let's take a look at the first application, the NASDAQ market filtering. We connected a server to a Tofino programmable switch. And on the server, we ran a feed publisher which sends market events to the switch, which sends it back to the server, which has a subscriber running on it. The subscriber is co-located on the server with a publisher for accurate timestamping. And the subscriber is only interested in events for the Google stock. We measure the baseline latency for the switch to forward all the packets to the subscriber and have the subscriber perform the filtering. And then we ran packet subscriptions on the switch and had it do the filtering instead. So what did we find? This CDF shows the end-to-end latency. We can see that the baseline has a large tail latency. 30% of the packets arrive with a latency from 10 microseconds all the way to 300 microseconds. When the switch filters the messages, the tail is a lot smaller, as you can see on the green line. The 99th percentile is below 50 microseconds. And this is because the buffers don't build up at the subscriber. When the subscriber is performing the filtering, it cannot keep up with the line rate. The switch, however, can perform filtering at line rate and send exactly the packets that the subscriber wants. Thus, the subscriber does not waste any time filtering out the superfluous messages. All its cycles are spent usefully on packets that it actually wants to receive. The last question we had is whether routing or whether memory is used efficiently. And to evaluate this, we use a realistic workload for filtering market events. We measured how much memory is used at the core, AG, and TOR switches. And then we compared the traffic reduction scheme to the memory reduction scheme, those routing schemes I showed you a few slides ago. We found that overall, the compiler uses memory efficiently. With 1,600 filters, we can filter the prices of a few hundred stock symbols, which is a realistic workload. And this generates 18 million table entries, which fits well within the memory constraints of the switch. Notice that here in the traffic reduction scheme, that all the switches use the same amount of memory. And this is because, as I mentioned before, every switch in the network needs to store every rule to send the packet the most direct path. With the memory reduction scheme, on the other hand, most switches use very little memory. That's because they only need to store subscriptions or the rules for the hosts that are immediately below them in the topology. The core switch, on the other hand, needs to store all of these rules. As you can see, the curve here for the core switch is the same as what we saw for the traffic reduction scheme. So there's no difference in memory reduction between the two schemes, at least for the core switch. So in conclusion, packet subscriptions provide the abstraction that applications actually use. And in doing so, it reduces latency experienced by the applications, while also being able to handle higher throughput than software-based middleware. And this is done using network resources efficiently, both in terms of the switch memory and traffic. We've also showed that packet subscriptions can scale to large data center topologies. We invite you to try out packet subscriptions. We've open sourced our compiler, and we also have a demo that you can try out right on your own computer. You just need a Docker container. We also hope that packet subscriptions will foster the emergence of new types of applications that require expressive, low latency messaging that wasn't previously available. Thank you. I'll take any questions that you could have.
Yeah, we can maybe we have two people in the queue. First is Alexander Clem. So Alexander, please ask your question.
Yes, hello. Very interesting presentation. Thank you very much. My question is what you can actually filter on. Basically, does it require you to inspect payload, or how do you deal with encrypted traffic? Can you comment on that?
Yeah, that's an excellent question. So our compiler, you can specify to our compiler the packet header format using P4. And so any header format that's parsable by P4 is supported by our compiler, essentially. And so, of course, there are some limitations. So how deep you can look into the payload and what types of header formats. So since P4 supports fixed length, fixed width headers, that's for now we're limited to that. And I think you mentioned something about encryption. That's something we're also, of course, lots of messages that travel through the network are encrypted, and that's unless the switch can decrypt packets. Right now, packet subscriptions needs to look at the packets in plain text. And we've been thinking about some homomorphic encryption schemes which will allow the switch to perform forwarding on these packets without knowing the actual content. But that's we haven't made much progress on that front. Did that answer your question?
Yes, thank you.
Dirk?
Yeah, thanks. Very nice presentation. I think it's a good example of, say, how the network could, assist in achieving, computation or data subscription like applications. So I'm a bit familiar with the general body of this PubSub work. And so I also wanted to ask the security question, but you already mentioned a potential way there. What about other things like congestion control, for example?
That's a good question. So I'd argue that congestion control is orthogonal to what packet subscriptions does. I think that you could add congestion control to packet subscriptions. And another issue related to congestion control is reliability. And again, that's something that's difficult to handle in publish subscribe systems, especially because unlike models like TCP, which have one sender or one receiver, in publish subscribe systems it can be one to many or many to many model. So you don't. It's if a client doesn't receive a message, or end host doesn't receive a message, it's not clear whether it hadn't subscribed to that message or whether there was a packet loss in the network. So I think congestion control should be handled at another layer than packet subscriptions.
Okay. Thank you.
I know there's a question from Dave Oren, and I see now there's somebody else who joined the queue, but for sake of time, Tianji, maybe you can be very fast. And Theo, you may want to look at the question from Dave Oren and respond offline. It's about fragmentation. So Tianji, quick question, and then we move on. Okay. Okay, then
Hello?
if
There you
Tianji
go.
is not,
Hello? Can you hear me?
Tianji, we don't hear you.
We can hear you now. You're a little
Oh, okay,
quiet.
good. Yeah. Oh, how about right now?
Yeah, go ahead, but please be quick because we're taking too much time.
Sure. Sorry about that. It's just like informational, very interesting topic. But just for the example you are using here with NASDAQ example, you may reference a paper by Austin Gregg from SEC about some fast. The slowness on aggregated transactions. So in your case, you are doing some round trip between the server, your switch, and then subscribers. So it might cause some problem with the things. So there's a paper about how to do this type of things. So you may reconsider your example used in your presentation.
Could you please write that in the chat?
Type that in the chat, yes.
Yeah, that would be
okay, sure.
as well. Thank
Okay,
you.
sure. Yeah, it's like a 3 year back. Yeah, from SEC. Okay.
Thank you.
Yeah, please put the paper in the chat. Diogo, I hope you're back.
But before you go, Theo, thank you for an excellent presentation.
Yes, and yeah,
great.
thank you, Theo. And I'm sure there's going to be follow-up. And Diogo is starting to share. and hopefully the sound will be there. So Diogo, you don't have to restart from the beginning. You can go to where you were when the sound went off. And I remind you that you have 15 minutes. You have way too many slides. So hopefully things will go better this time. And we still have issues. And Diogo's offline, so that doesn't work. Okay, so so
I'm back, so I hope I can try to share now. So I'm sorry. Can you let me know where I lost you?
I think you were on slide 7 or 8.
Okay, slide 7.
Yeah, so hold on.
Should be here.
Okay, let's start there, and that's fine. Yes, you were there because there's pictures that come into that. But I remind you, you already were at 8 minutes, so now we're going to limit you. So go fast through the contributions and go try to.
Okay, so I'm going fast and skip some of the details of the implementation.
Yeah, thanks so much.
Thank you. So we propose Flow-Lens, which is this flow classification system for generic machine learning-based security tasks. And one contribution is this compact representation of the packet distributions within the switch. The flow marker accumulator, which is a way that we actually implemented this kind of a collection within the switching hardware. And then we built an automatic profiler that can tailor the size and the accuracy of these flow markers respective to the application itself. And so we also evaluated our system, resorting to 3 different security-based tasks. So in a nutshell, our Flow-Lens system is comprised of a profiler server, which can be used to, given a training data set provided by the client, tell us which are the better parameters for achieving that balance between the size and the accuracy of the flow marker. These parameters will be loaded into a P4 program within the switch that will be responsible for actually compressing the packet distributions. And periodically, these flow markers will be collected to the control plane of the switch, which will be actually performing the classification of these flows. So Flow-Lens can be used distributed fashion across the network to scale the number of measured flows and ensure network visibility, and can also be used in different switches to support multiple machine learning-based applications across the network. So to produce these packet distributions efficiently, what we did was to quantize the packet distribution. And so in some sense, you can see that if this is the raw packet size distribution of a given flow, we can compress it, let's say by a factor of 16. And then we can further apply a pre-processing step based on supervised learning that will tell us which of these particular bins of the distribution are most useful for performing classification. And so in this case, we can see that this is the top 10 bin that will be still useful for representing the actual raw packet size distribution and still achieve a high classification accuracy. And so, for instance, this allowed us to achieve up to 150 times size reduction in the size of these flow markers. So just for the implementation of flow marker, I would like to say that we started by implementing our design on a software simulator, and then we had to adapt our program in a physical switching hardware where we actually focused the Tofino switching ASIC. So I'm going to skip some of the problems that we did have in implementing these on the switch itself, but I would like to let you know that the typical architecture for one of these programmable switching devices is actually these sequence of match action tables that can match some packet fields and trigger an action that will change some packet headers or metadata. All this is programmed in P4, and there are a few drawbacks on this feed-forward pipeline that we had to overcome to actually build our quantization and truncation approaches for generating flow markers. So I'm skipping some of the details of this implementation that basically show that we actually had to come up with a representation that was simple enough to be run in these tasks, and that we actually used the control plane to assist in this truncation procedure. So in a nutshell, I'm going to show you how what happens in Flow-Lens when a new flow actually reaches the switch. So suppose that we have this flow ID that the switch has not seen previously, and the packet size of that particular packet of the flow is 512. Since this packet has not been yet seen in the switch, we will ask for the control plane to install a rule that will index this flow in the flow table that is in some of the stages of the switch. So the flow will be indexed, for instance, here in stage 4, and we also use the control plane to set a flow offset in the register grid, which is the amount, the local in memory, where we'll keep track of these flow markers. So in stage 1, we will quantize the distribution, and so we will obtain a bin index of this quantization from this packet size that corresponds to 16. In stage 2, we will perform the truncation process and consult the table that was set previously in the control plane. And in this case, the truncation flag is set to 1, which means that we should keep this packet size, and the bin offset is 1, which means that it is the second packet or the second bin that we should take into account. So in stage 3, nothing will happen because the flow does not match in this flow table, but it will match in flow table 2 in stage 4. Once this happens, we can compute the cell offset that should be updated in the register cell that corresponds to the flow marker of this flow. And so we do this by summing the flow offset with the bin offset that was computed previously. And finally, in stage 5, we just increment the position for this particular flow marker, and this allows us to count and to generate these flow markers at line speed. So since there is this large configuration space of quantization and truncation parameters, we actually leverage Bayesian optimization to build an automatic profiler that could build these flow markers with 3 different criteria. Either choose the smaller flow marker for given target accuracy, to select the best accuracy given a size constraint for the flow marker, or else to find a compromise between the two. And by doing this, we actually save many hours of testing what could be suboptimal configurations of the parameterization of quantization and truncation. To evaluate our system, we try to evaluate its scalability on 3 different generic machine learning-based security tasks, including cover channel detection, website fingerprinting, and botnet detection. We evaluated the performance of our profiler, and we also evaluated the resource consumption that Flowlens used in the switch, both on CPU usage and also on the ASIC usage. So these correspond broadly to the cases that we studied in our paper, which I will not briefly cover for interest of time, but we can check it in our paper as well. So in a nutshell, the scalability gains of Flowlens can be seen in this table. So for instance, for the use case of cover channels, we are able to scale the number of measured flows simultaneously in the switch by 150 times, while losing only a 3% accuracy loss in the performance of the task itself. And for instance, we could scale the number of flows measured in the switch by over 30 times, both for website fingerprinting and botnet detection, while losing also just 2% accuracy, or for instance, 2% precision in the performance of the classifier. In the interest of time, again, I'll just cover briefly our results for cover channel detection. So one thing that we can see here is that, for instance, depending on the quantization level, we'll be using less and less memory for keeping the raw packet size distribution, which also allows us for keeping track of many additional flows. So for instance, here we can see that with full information, we will require 3,000 bytes to keep packet size distribution for just a given flow, and this will allow us to perform this cover channel detection task with a 96% accuracy. When we use quantization, for instance, with level 4 and shrinking the size of the distribution by over 16 times, we can see that we could keep the same information in just 188 bytes and still achieve a detection rate of about 92% accuracy. Further, by truncating this quantized distribution, for instance, by just selecting the top 10 most important features out of the quantized distribution, we are still able to detect the same kind of cover channels with 93% accuracy, and using just a representation of this packet size distribution that only takes 20 bytes. And so effectively, we are having an increase of 150 times in the number of measured flows. We've also seen that the Flowlens profiler is able to find a good quantization and truncation parameters. So I'm also just trying to show you here that despite other configurations that may achieve a higher accuracy in the task, so for instance, using a quantization level of 2 without any truncation would give us 96% accuracy. But if we use our profiler to choose a sensible trade-off between the size and accuracy, we can actually achieve a configuration which uses a quantization level of 4 and a truncation level of 10 features that still achieves 94% accuracy. So just 2% less than this optimum accuracy-wise. We've also seen that flow length imposes only a small overhead on the switch. So for instance, when using CPU, we've seen that for instantiating our botnet detection model, which was also actually our largest model, we just use 140 megabytes out of a total 32 gigabytes of RAM. We just required 5.6 megabytes of storage, and we just wasted around 200 microseconds per prediction. However, we can see that this allows flow lengths to support the flow classification in the control plane itself. And as for the ASIC usage, we can also see that we do not use TCAM at all in the switch, because we just really require the use of some SRAM to keep these flow markers as they are being processed and computed as new packets are flowing through the switch. And we also do not use many computation resources of the ASIC, which also means that flow lengths can support the concurrent execution of other forwarding behaviors. So I'll just like to let you know that our experimentation artifacts are publicly available. So we made available this P4 implementation of the flow marker accumulator, and also provided a test bed for these 3 different machine learning based tasks that we covered in the talk. So I invite you to check our code. And before closing my presentation, I would like you to keep in mind these 3 big takeaways, which is that FlowLens is the first traffic analysis system for these generic machine learning based security applications in programmable switches. That is able to collect these compressed packet distributions while ensuring both classification accuracy and a small memory footprint of these flow markers. And it is also able to classify the flows directly on the switch, disregarding any additional infrastructure, which enables us to save communication, compute, and storage costs. So thank you. I'll be available for answering any questions. And I have also an additional slide that I hope that can spark some discussion relating to some other killer apps that you can think of for FlowLens. And some other general questions of whether you actually deploy P4 code into Fino, and what difficulties did you face actually. Thank you. I'll just
Thank you very much for this.
Try to spawn my video here.
Great
I'm sorry.
presentation. Do we have any questions in the queue? Actually, I don't see any questions, so I will ask people to move their questions to the list. Thank you very much, Diogo, and
thank you.
I understand all the problems with connectivity. Since
I'm sorry.
I had a ton of them too. So thank you so very much for living with that. The next presentation is, if I had my my things well done. God, I have too many things. So the next presentation is from the University of Toronto. Sayed, Sayed, are you there?
Yes. Can you hear me?
No, actually, next one is Harshit. Sorry, Sayed. I skipped over Harshit. I know Harshit is there because I saw him in the chat. So please, Harshit, it's your. Please present your paper.
Sure.
And then Sayed, you're next on deck. So we'll be done.
Okay. Hello, y'all. Thanks for the opportunity to present. I'm a PhD student at Georgia Tech, and I'll be presenting our work on data management over geo-distributed edge computing infrastructure. This is a work that I did with my advisor, Professor Umakishore Ramachandran. So at the edge, we now have these novel applications which are springing up, like collaborative driving assistance, distributed camera networks, autonomous drone swarms, etc., which pose new stringent requirements on the infrastructure. Some of those requirements are enumerated here, like they have geo-distributed clients, they require low latency access to compute services, they generate data at a very high rate, and they are characterized by continuous mobility of clients. These are typically good use cases for edge. So our vision of edge computing is the following, where we have a continuum of resources ranging from very proximal resources close to cell towers all the way to central offices and the cloud. And these resources could be owned by the same or multiple providers. As you can see, there's a dense geo-distribution of sites, and due to space and power constraints, each site has limited resource capacity. So the applications that we discussed before require managing data, because as we just saw, they discussed, they generate a lot of data that needs to be handled. So what are some examples of data? So for instance, information that is generated by one application could be used by others, which is like the use case that Nokia streaming as a service was promulgating. Another use case is time series, wherein data can be stored in a data platform, which can be retrieved later for historical queries or for analytics. Another form of storing data is to store the state of a processing workflow, which is done in stream processing platforms like Flink. In addition to data, which is persistent, we also deal with communication between entities. For instance, drone swarms need to communicate with each other to coordinate for a given task. That also holds true for collaborative driving, where multiple cars need to fuse their sensor data to get a more extended view of the world for better obstacle detection. So what are the typical solutions which have been used in, say, the cloud computing space for data management? So if you think about key value stores, which suits the first set of use cases, Cassandra, Timescale DB, and InfluxDB have been typical platforms which have been used for maintaining data for these for applications. For real-time messaging between application components, developers have traditionally relied on PubSub systems like Pulsar, Kafka, or MQTT. However, at the edge, there are some requirements which are kind of novel as compared to data center data management platforms. And that is, we need to provide low latency and high throughput access to data. The data platform should be agile in such and adapt to workload dynamism, for example, client mobility. And it should also expose well-known semantics to clients so that application development is a better experience for developers. So if we just use the cloud-based platforms on the edge, there are a number of problems that arise. So the first problem stems from the fact that the topology of edge is highly heterogeneous. Systems like Cassandra or Pulsar typically use a hash function for partitioning data among various nodes. So this diagram shows the way Cassandra works, wherein it takes the key of the key value pair that it needs to store, it hashes the key, and based on the hash value, it assigns it to multiple nodes, that is the primary and the secondary replica. But this process, as you can see, is agnostic to the topology, and therefore can perform very poorly in a geo-distributed edge setting. The second problem with edge, a challenge with edge, is that the geo-distribution is very dense as compared to multi-data center deployments that we typically see for databases, and therefore granularity at the level of racks is not sufficient, because we would need to also attribute location or some kind of network proximity information into our data distribution policy. And finally, there is no support for monitoring client mobility, and thus these solutions, they don't have any mechanisms to handle workload dynamism that are peculiar to edge computing. So in our area of research, we try to build edge-friendly data management solutions, and which tackle the above challenges. And in this talk, I will be briefly going over two systems that we have implemented, which cater to different classes of data management, and how we incorporated edge-friendly mechanisms into them. In both cases, we assume that the data management platform is deployed on multiple edge sites, such that there is one platform which is running on top of a continuum of edge resources. So let's first begin with a description of Datafog, which is a geo-distributed spatiotemporal key value store. This platform provides a user interface that is similar to typical key value stores, wherein you can have keys and values. And in addition, the developer can specify the location of the data item and the timestamp of that data item. So this is a spatiotemporal extension to typical time series databases. And the assumption of this work is that we are dealing with situation awareness applications like autonomous cars or autonomous drone swarms or navigation assistance, wherein low latency data is required by clients which are in proximity to the data item. That is, we don't guarantee low latency to an arbitrary data item, but only to those which are close to the clients. And we implemented data fog by extending Apache Cassandra. So before we dive into the design choices, let's quickly go over the sources of latency in geo-distributed key value stores. The first source of latency is the selection of replicas. So as we just discussed, Cassandra uses a hash function, which in this case is consistent hashing, to determine the location of replicas for a given data item. So that is not aware of the network topology, and therefore it can be highly suboptimal in terms of latency. In addition to that, these databases, in order to provide consistency, they perform replication in a synchronous manner. And since even all the replicas are not close to the client, it results in higher latency to perform reads and writes. So these two sources of latency drive us to make the design decisions for data fog. The first is that we incorporate location-based data partitioning. The objective of this design choice is to keep data close to the potential users. For example, a smart car is interested in congestion information of the same city because that's what is relevant for it. So therefore, storing data for that city close to, on an edge site, within or close to that city will provide low latency access to those data items. And how do we do that? So in Cassandra, we modify the hash function which has been used by Cassandra to convert a data item to the partition key, which is used to figure out which replicas to select for that data item. We incorporate location information into the partition key by using a well-known geoencoding technique called geohash. So that provides a prefix for the partition key from the location of that data item. And therefore, now we can we can use the same hash ring mechanism in Cassandra, given that now the output of the hash function is location sensitive. And this allows us to place data items closer to the location that that data item corresponds to. So in addition to location-based partitioning, we address the other source of latency, which is synchronous replication for high consistency. To do this, we utilize spatiotemporal locality in queries. So going back to our assumption, a smart car is interested in recent events in its vicinity, and we provide consistent access to spatiotemporally relevant items. That is, we ensure that the read and write quorums overlap. This relevance is specified by the developer by an abstraction that we expose to the developer, which is called area of interest, which is specified in terms of geographical distance. And all data items which are within the area of interest for a given client are considered to be relevant. For instance, in the example, if the car at a given location has an area of interest, which is defined by a radius, and all data items falling inside that area of interest will be available with strong consistency to this client. So given that, we have now the luxury to maintain two types of replicas. We maintain strongly consistent replicas in vicinity of the data item so that we can provide low latency access to clients for whom that data item is relevant. And we also maintain remote replicas, which are eventually consistent, and for data items which are and we can provide fault tolerance from correlated failures, because it is more likely in an edge setting for sites to fail in a geographically correlated fashion. So having a remote replica helps in that case, although it's not strongly consistent with the in-vicinity replicas. So we show that such optimizations provide, such locality optimizations provide significant improvements in reads and write latencies. So we experiment with a data store infrastructure where we have 4 data store nodes which are local in Atlanta, and there is a variable number of remote data store nodes which are spread across the US. And the emulation has been performed using ContainerNet, which is similar to Mininet, but that uses Docker. The query is a range query that selects all vehicles within a 5-kilometer radius that were detected 10 minutes ago. And we see that as you increase the scale of the data stored by adding more remote nodes, the access latencies increase. And that is because Cassandra, and that is because Cassandra is not aware of the network topology, and therefore it places replicas in an agnostic fashion, which results in high data access latencies. However, since data fog is completely aware of the location of nodes, it is able to consistently maintain the access latencies at the same level as a very small scale cluster. So with this, let me move on to the next data management system that we will be talking about. That is a topic-based publish-subscribe system, which is designed for the edge. We call it ePulsar, and it is under review at this point at the Symposium of Edge Computing. So ePulsar is a geo-distributed publish-subscribe system, and it follows a similar interface to Kafka and Pulsar, which are also commonly known pub subsystems, wherein producer clients publish to topics, consumers consume from topics, and brokers are system entities that host those topics. And ePulsar allows developers to specify per topic latency constraints. That is, the end-to-end publish-subscribe latency should be below a developer-specified threshold. So what are the sources of latency in typical publish-subscribe systems? So as before, since Pulsar also relies on consistent hashing for distributing topics to brokers, it does not take into account network topology, and that results in high client-to-broker latency. That is, the latency between the producer and broker, as well as between consumer and broker, is unpredictable and can be high because of the heterogeneous nature of the edge. So in order to solve this, we make two main contributions. We first incorporate network coordinates, which is a well-known decentralized P2P protocol for scalable internode latency estimation to estimate client-broker latencies without much overhead. And secondly, we incorporate the network coordinates into the broker selection algorithm so that we can minimize the worst-case end-to-end latency. In addition to that, this placement or this selection of brokers is adaptive, and it can adapt to continuous client mobility. We implemented ePulsar by extending Apache Pulsar. So first, for scalable client broker latency estimation, we run a network coordinate agent, which is running the well-known Vivaldi protocol on all system entities, which is the producers, consumers, and the brokers. As the implementation, we used Surf network coordinate agent as the building block for this entity. So these network coordinate agents, they interact with each other, and then they converge on a network coordinate in a high dimensional space, such that the distance between two network coordinates gives you the latency between those two nodes. So it is a very scalable way of estimating internode latencies. So then once each system entity knows its network coordinate, the clients report their current coordinate to the serving broker, and broker aggregates these monitoring pieces of information from all clients, and then they send it to the control plane, where we use this for initiating topic migration if necessary. So the worst case publish subscribe latency can be visualized as the maximum distance between the network coordinate of any producer to the current broker to the farthest consumer from the broker. So this distance gives us an estimate of the worst case publish subscribe latency, which is used by the control plane to decide if it is greater than the threshold or not. And if it is, a topic migration is triggered, and the new broker for that topic is determined by a latency aware broker selection algorithm. So for that, we use an aggregate of the producer's network coordinates, which is namely the centroid in our case. We use the centroid of producer coordinates and the centroid of consumer coordinates to estimate the worst case latency that can be experienced, that can be provided by a candidate broker. And we select the one that meets the latency constraint. So we show our evaluation. I'll be quick with this. So this is a UAV swarm scenario where there are multiple drones which are talking to each other, talking to the leader and the leader to the follower by using the PubSub interface. We evaluate this in a city-scale infrastructure with multiple sites. And on the bottom, you can see a time series of communication latency for each drone swarm. As you can see, there are certain spikes, which is when drones move from one side to the other and incur high latency to the previous broker. And ePulsar is able to mitigate that by performing topic migration. So in conclusion, we design edge-friendly data management solutions that solve challenges posed by the edge on contemporary data management platforms, and we show how these two work for key value stores and pub subsystems. And following are the references if you'd like to check them out. And that's all for this talk. Thanks for listening. I can take any questions that you may have.
Thank you very much for this presentation.
Yeah, I have a question.
Yeah, actually, Jay, you have a question. Jeffrey, I will let it to you.
Okay, so thank you for your presentation. So you mentioned in your first system that there are two parts of latency. When you select the replica, and the other is synchronization replicas with consistency. So I think both can be potentially improved by innovation inside the network. But what is the major one in between these from end-to-end point of view? So which latency is a major latency? Synchronization or select the replica? Make that decision.
Yes. So the major source of latency is the synchronous replication, but that is tied to the selection of the replicas because it depends on where the replicas are located. So we need to so if you don't do the selective replication, in that case you pay the penalty of going to the farthest replica, and that also imposes high latency on the overall access. So I would say it's a combination of both.
Okay, thank you. So Dirk, next question.
Any other questions? Oh, Dirk, please.
Hey, Hashid, thanks for the presentation. So in general, I think you are on a good track. So I think there's good potential in, finding out how these relevant application layer systems and their interactions can be better supported by the network. But in your system, I was wondering, so mostly when we do, networking and optimization, we are interested in, say, good performance and efficiency from a topology perspective, so network topology, not so much geography. So in most cases, it matters more, what is the hop distance to some information source, compute function, and so on, and not so much what is the closeness in terms of geographic coordinates. What's your view on that?
Yes, I totally appreciate your question. So that is one reason why we move from a geographical location-based approach to a more, network coordinate-oriented approach, because by using network coordinates, it is agnostic of location and it gives you proximity in terms of round-trip time. We don't consider hops because we don't assume that as edge provider, you would know about the internals of a network, of the network. Say you are an edge provider like MicroEdge, which is deployed on peering sites. So we just care about end-to-end RTP, and based on that, we can make these placement decisions.
Yeah, okay.
So thanks, it's a great question.
Thanks.
Any other question? Okay, so then thank you very, very much for this presentation. And then now we're back to the next presentation. So please, Sayed.
Yes. So can you see my screen?
Yeah, but I saw that it was going to be presented. Can you try sharing again? There we go. No problem. Back to the problems.
Okay. So
Yes,
I suppose
great,
that you
thank
can
you.
see my.
Yes.
Okay.
Yes, thank you.
Okay, so the topic of my talk today is hierarchical data storage and processing on the edge of the network. This was a collaborative work with, at University of Toronto, this was my PhD work, and with some folks at AT&T Research. For the past 15 years, cloud computing has transformed the means of computing and data storage by providing scalable, flexible, and agile computing and storage services to users, applications, and businesses. However, current networks are not able to support next-generation applications that require low latency, such as AR, VR applications, wearable devices, and safety-critical applications. Or applications that produce large volumes of data that can overwhelm the network, such as video analysis and IoT devices. And they also don't support other applications that have other requirements, such as specific privacy requirements or exact location detection or scalability. So our idea is to apply the same principle by enforcing a clear separation between computation and state. To address these challenges, edge computing proposes the addition of computation and storage capabilities to the edge of the network. We assume that edge computing networks are composed of a collection of hierarchical data centers, as you can see in the figure. And with edge computing, additional services could be provided to applications such as the location, authentication services, mobility management, and so on. So to emulate the success of web applications on the cloud, we should understand why these applications have worked so well on the cloud. And what we see is generally that many web applications are partitioned into independent state handlers. And each request is processed by a different handler. Now, in this model, requests don't necessarily go to the same server, but what enables this model to scale is a shared storage layer where all handlers can share state. Now, as I said, our idea is to apply the same principle by enforcing a clear separation between computation and state for applications. And we propose CloudPath, that is a new model for deploying and executing third-party applications on the edge of the network. In CloudPath, application developers organize their applications as a collection of stateless handlers, and CloudPath deploys and executes those functions on demand over the hierarchy of data centers, replicating application and code data. So each CloudPath node that is deployed on a separate data center contains the following modules: a path execute that executes functions in an isolated environment, path deploy that deploys the applications on demand, path routing that routes requests to running functions, path store, the common storage layer responsible for moving application data and code, and finally path monitor, which is the common monitoring platform. Now, to show how CloudPath works, we present an example. Consider an application that controls a swarm of drones over a city that includes 3 functions. The drones carry a camera, and the application includes an object avoidance function, and a function that records flights info, and then function that receives sensory data and makes decisions about the flight path. So the application developer may require the object avoidance functionality to be close to the drones because of the lower latency and bandwidth. And when a new request comes onto the function, it goes onto the edge. CloudPath copies the application code and executes the application on that node. It also runs the code on the edge's parent all the way to the cloud. Similarly, the developer may want F2 to run on the cores, where data from different drones can be aggregated, and F1 to stay on the cloud because of the infrequent latency insensitive nature of the requests. On each node, multiple functions from different applications can run on the same time. But the code and data application is only on demand. So if we can have another application app2 that runs on the cloud and can be replicated on Core 2 on demand if a request comes in on Core 2. Compared to running an application on the cloud, there's a significant improvement, as one might expect, in terms of request response time when running an application closer to the user. In our experiments, we deploy a face detection application using CloudPath, and the results show that it has a big effect on resource and code placement. What a big effect resource and code placement can have on query response time and potentially throughput. However, one thing that we haven't really, I made this slide for this talk. Something that we can significantly improve on is routing overhead. In CloudPath, we use information in an HTTP header, so it's layer 7 routing. Route requests to the related execution points. However, this can be significantly improved. Now, our second line of code work is PathStore. It's a component of CloudPath. PathStore is a data storage layer for a multi-tier cloud architecture that supports storage on a progression of data centers deployed over the geographic span of the network. The goal that we have with CloudPath, to realize the path computing objective is to, as I said, to provide the common storage layer for edge computing applications. Now, PathStore is composed of a hierarchy of independent object stores. And in our implementation, each node runs a Cassandra ring, a full Cassandra ring, which means that we can have horizontal scaling within a data center. Essentially, PathStore is responsible for replicating data between these different object stores through background processes. Now, it supports eventual consistency. However, our extension, which I will talk next about, called Session Store, supports session consistency, read your own writes, monotonic reads and writes for users and devices that use this service. So in PathStore, the node at the root of the hierarchy contains all persistent data, and all other nodes act as temporal partial replicas. Data is replicated on demand when a query comes in. However, and this is the most important part of the whole system, is that all reads and writes are executed locally against the local database. And as I said, background processes move data around. If a key doesn't exist at a cluster, then it is obtained through a traversal up the tree until we find the key. And writes to keys are written on the local data store and periodically propagated up to the cloud node. We use a SQL-based interface, and in our implementation, we use Cassandra as for each ring, and we have row-level replication. Now, as an example, suppose that we have an application that has a table called marbles, where the color of the marble is the primary key. Now, assume that some data already exists in the cloud node. If a user executes the query select all for marbles where color equals blue on edge 3, because edge 3 does not have the data, the query is executed on the parent node. As core 2 also does not have the data, the query is executed on its parent node, which is the cloud. This process continues until we reach the cloud, and then the data is replicated on all nodes on the path from edge 3 to from the cloud to edge 3. So the blue marble is replicated on core 2 and then edge 3. A similar process is repeated when edge 1 does a select all from table marbles and data is replicated on core 1. And then data is received on edge 1. However, when edge 2 executes a subquery, selects all from marbles where color equals green, rather than going all the way to the cloud, data is obtained from core 1. In the case of writes, when an object is written locally, it's periodically pushed all the way to the cloud. So as I said, the cloud contains it's a persistent data store, and a pull daemon running in the background on core 1 and edge 1 periodically re-execute the query that was previously there, which is select all from marbles. And they're able, in this way, they're able to fetch new data. So the results in the red marble, for the red marble automatically is replicated on core 1 and edge 1. Now, edge and intermediate nodes in path store, as I said, act as cache. When data exists on them, reads and writes fast. In this specific experiment, we examine how long it takes to answer a query on the edge or core and cloud nodes when data is cached on local path store nodes, which is the orange bars, and compare it to when data does not exist on local nodes and has to be fetched from the cloud, which is the blue bars. And we also compare it to a scenario where data has to be fetched from the cloud node without any path store. It's just one single database, one single Cassandra database. So you can see the benefits for reoccurring queries. Now, our next work is on providing stronger consistency guarantees for the edge data storage layer. Edge users and devices are commonly mobile and can move between data centers. This means that their data has to move with them in a consistent manner for many applications. In this figure, we have two scenarios where the session consistency for a mobile user is broken. For example, a client writes a value on a server on edge 1, then moves to edge 2, but reads an old value. So what we want to provide in this line of work is read and writes and monotonic reads and writes. Now, we build session store on top of path store. Session store ensures session consistency between different edge nodes and does so by grouping related data accesses into a session. And using a session-aware reconciliation algorithm, which I'll explain, it only reconciles the data that is relevant to that session. Again, we have row-level replication. So as an example, a user on edge 1 executes 2 queries and then moves to edge 3. So select all from marbles and inserts green marble into the marbles table. Then it moves to edge 3. One approach, the DOM approach, is to move all application data, including the stamps table, to edge 3. Our alternative is only to move data related to the session, which is some rows on the marbles table, to edge 3. So all of the data is fetched from edge 1 directly, but it's only the data that the session has accessed. Now, if there's some data already existing on edge 3, we only need to move the newer data. So a delta list optimization only moves newer data. We also have an optimization for when a user moves to a neighboring node. In that case, only data that was read or written on edge 1 and has not been updated on core 1, which is the parent, is sent to edge 2, as the other data can be can be queried from core 1. So if the application needs the blue marble, rather than transferring all the session data from edge 1, we know that it can get it from core 1, so it just fetches it from core 1. So each session in session store is identified by a token, which we call an S token. It's encrypted and signed to prevent forging or misrepresentation. And what constitutes as a session, we leave that to the application developer. To keep track of data related to a session, a command cache is added to each path store replica that stores all the statements that were executed on behalf of the session. And we use a benchmarking application that models a discussion board to test the performance of our system. And as shown in the figure, our optimization, a session-aware computation approach where all data related to the session is sent to the destination edge, and the delta list optimization that only sends the differences between the relevant it only sends the relevant data. They use significantly less data compared to the full reconciliation approach. For discussion, I've included some points that I think that would be relevant to the network. As I said, first of all, in CloudPath, routing requests for applications functions can be smarter. We use layer 7 HTTP headers, but that can be significantly improved with in-networking routing that are aware of the functions. Also, even for eventual consistency, path store needs synchronized clocks between data centers. This is again a service that I think that the network can provide, so that we are sure that the clocks are synchronized. We can assume that there's a GPS clock on each data center, but even if there was nothing there, I think that the network can provide this service. And I also think that we can move entirely or create a service, a locking service for data consistency. And then if there is such a service inside the network itself, then better guarantees can be provided by data source. And with that, I conclude my presentation, and I'm ready to take questions.
Yeah, we'll push all the questions to the chat because we're really getting out of time.
Sure.
It always happens. Anyway, Edgar, are you still there?
Okay, yeah, I'm here.
So,
let's see. Screen comes. Can you see it?
Yes. Thank you.
Yeah. Okay, well, hello everyone. My name is Edgar Ramos. I'm a senior researcher at Ericsson Research. And today, well, my presentation is a bit different than the one you have been listening so far. It's more about, I would say, research questions for us for the future, and how we have a vision toward how the things are going to be transforming the way how the network is today and what it should be addressed in the future. This is part of some work that was done in a crowdsourcing way in Ericsson research by pretty much all the research areas we have, and where everyone with their knowledge and their, let's say, skills in their area and expertise they contribute and then provide this kind of information and input. And then what I'm going to show you is how we believe that these intelligent machines are going to evolve and how the network it will evolve with it. So to put it a bit on context, one of the things we were kind of we were considering is what are the things that are driving these changes. And of course, we have the weakest connectivity as the main main thing where when everything gets connected, then it gets the power to get exposed to everywhere else. Then we have IoT and all the devices that are interacting with each other and with humans. And then when we add on top of that AI, and then all the capabilities that AI are bringing, and I'm not only talking about machine learning, but also the trying to almost mimic human behavior and even further than that. So, I mean, not only becoming machines with human capabilities, but even capabilities that goes beyond what the humans have. Then we have the cloud and edge that are coming, then also the trustworthiness and how we can start to trust not only data, but also processes and machines. Then we have the robotization, the new ways of interaction with machines, so how the humans are able to communicate with other machines. And then finally, we have the new computing paradigms, alternative materials and energy technologies, so that are becoming more and more common in our everyday lives. And they are starting to permeate these 10 forces, and together they are kind of leading or creating this kind of path, which we call the technology journeys. Then to put it a little bit on context to COIN and what we do in COINRG, the network should match or will match this evolution of the machines. So the machines as we know them today, a refrigerator, a toaster, or very simple machines, even our cars, it will evolve to something much more complex, and with it becomes more autonomous, and it will become also more generic. So our device will stop being a specialized thing, but it will actually start to do more things that it was designed to do as an initial, let's say, a purpose. Then also, this will mean that we will have all this customization going around, because at the same time that the things are generic, they also have to address so many new use cases, adapt to what is happening, that this kind of need for customization is something that will be there. But still, we require this interoperability. The things should talk to each other, and then that's something that the network should facilitate. Additionally to that, then we have this empowering the devices by the network, by discovery, exposure, trust, self-organization, things that we know that the network could already do. But even beyond that, when everything becomes intelligent, so then there will be this need for mediation and arbitration of these kind of agents that are running in the machines, intelligent agents. Then finally, we could even question if the network is really relevant in the future when you have all this AI talking to each other, and then they might even think like, why should I use the network services? Maybe I can just create my own network services since I'm so intelligent. So, I mean, we could think to that extreme, but I think it's the task of the network to keep the relevance and improvise the incentive so that all this intelligence build on top of what the network can produce and not bypass it. So this in a nutshell is actually maybe the summary of what you're gonna hear, but I thought it was more interesting to maybe put it here in the beginning and then go actually to the journeys. So the journey I'm gonna talk is called Connected Intelligent Machines, and this is one of the examples of what we think in Ericsson it will be happening for 6G or the road to 6G. So we are talking about way to the future. And then we can start with basically two aspects. One is how the machines are going to evolve. So the machines, we think they will evolve from what we have today, which are machines that can have multiple sensors, has multiple different type of special ways to collect data. But at the same time, they are quite specialized in one domain. So they are not very generic. They basically, if you have a robot for a factory, most probably you cannot take exactly the same robot as it is and put it in another factory and expect that it will work perfectly. So you have to train it, you have to make it customized to the new factory where you put it. Then what we think is that those kind of robots and those kind of machines will evolve to something where the environment, depending on the environment and the sensing of the environment, the machines can adapt and can take intent instead of code for provide results. So today the machines, they require to be coded so that they actually do what you want them to do. Instead of that, they might give them just instructions or intents. Then we can go further to machines that learn from other machines, and then they even can control other machines. So one machine can maybe take over or understand what other machine can do, and then use it for the purpose that that machine has, the objective. Then we can take it still further, and I think I have been talking about mainly machines that are with an intelligence that is centralized, is in one place. But then imagine that those centralization then disappear, and then you cannot actually call one machine that is in one place, but is actually distributed in multiple places. And then that's what we call this decentralized intelligence, where multiple machines may actually work together, maybe in a swarm way, and they could resolve problems that otherwise they couldn't solve by themselves. Then the next generation could be something where the machines can actually rewrite their own code. They could even come to do their own training, and then even do their own life cycle management of software and decide what components they need to accomplish the task that they have been asked. Also, these machines could even change their own architecture. And they actually, there have been some studies and some work where machines are designing other machines. So all this is part of the journey. And finally, we could say about that the machines become more general. So they move from the domain-specific, let's say, field to something where they can actually handle problems that, and they could handle things or situations that are in multiple domains. And then these multiple domains could become something almost in the human level. So we could say that those machines maybe in the future could even pass an IQ test that a kid, a small kid of less than 10 years would pass. So then more or less in that level, we expect that the machines could reach maybe by 2030. So that is kind of the scope of this journey. Then the network should need to match this evolution of these machines. So we will have then data services that the machine would require to need for their specialized functions. And then that's what we have today. Pretty much we have all these data-oriented AI that is being feeding mainly algorithms. And then we have all this evolution where we go to discover the cyber war and navigation, how the network can provide APIs or can provide different services that allow you to find what exactly are the needs that the machine needs to fulfill. Also, we have these network services which are more specific for machines instead of humans, because if we think about the today situation, the networks are trying to fulfill mainly the human needs. And then here we are trying to produce services that serve or that are oriented mainly for machines. Then the native AI communications, you can think about, for example, the new technologies that use spiking neural networks or neuromorphic computing, where you have these new ways of communicating between machines using pulses or using brain-like, let's say, communication. And that is actually happening today. then we could even think about machines designing their own interfaces to communicate with each other, and then so that the communication could be even more, let's say, more optimal for them. Then what I was talking about, the incentive, is that the network should actually try to predict what are the things that the machines will need. What are the, trying to infer how can serve better the machines so that the network can keep relevant and can still be a part of the infrastructure that the machines are using, and then is not bypassed. And then finally, if everything is connected, if everything becomes part of a system of systems, so then this kind of mega brain, it's possible to be created, and then there will be unexpected behaviors that needs to be, for example, avoid, or it could be also that we need to do some arbitration or some kind of mediation between all these kind of different systems that might have even conflicting goals sometimes. Then in between, there will be a bunch of things that fills off also to this journey. I will take them in the next slide, but basically they are about interoperability, how interoperability can actually fill up the needs of the machines. Then the other one is human-machine coexistence, and then how the humans and the machines interact with each other. And not only that, but they coexist, because machines will require still at some point human input, and then at some point even collaborate with humans. Then a lot of what I have been talking with decentralization has to do also with system of systems, where machines will basically get together, and we expect that they will self-organize and then will create these autonomous systems where they can achieve goals that otherwise they couldn't achieve them if they would be alone. And then finally, the trustworthy part is very important, because it has to do with how we make sure that AI is safe. And it's not only about secure and let's say resilience, but also safe for humans, so that they actually do what we need, and not only for one human in particular, but even to society. Then, of course, you can ask me how this all gets together, and then that's what I will attempt to explain in this slide. So basically, if we take from each of the different, what we call stepping stones from all of these subjourneys, so then we can put them in this way. So for the first generation of machines, then we need still there will be a lot of this human machine assistance, this collaboration. Then we need to do this governance across the machine life cycle. So still we need to take care of those things in the beginning. But then towards we go to the more evolved machines. So new things are needed, like for example, semantic-driven communication in the interoperability part. So how we actually make the machines can understand each other, especially when they are learning from other machines. And then how they can expose their capabilities so that the other machines can actually utilize them. And then we also can see these kind of dynamic ways of interacting. So how a machine decides to interact with other, and then in one way create this kind of system of systems. And then finally, we also have to take care that whatever thing the machine does, it can be explained. And it should be a way that we can actually debug or understand how a decision or how something that the machine is doing, it can be traced to certain things. This environment and intent-driven machines are quite related also to this machine learning from other machines. And then there we also, the thing that is bringing forward is, for example, this intent and natural language and natural human natural way of expressing interactions. So then there the machines could take more from the environment, take more from a natural interaction with humans, and then fulfill their goals. Then when we are talking about decentralization, Then we have this, for example, conditional autonomy, where sometimes the humans are not in full control, but it might be that the machine takes total control in certain situations. For example, a car that is in a highway, it might be in this conditional autonomy mode. Then we have
Edgar, can you please conclude?
Oh, yes, I can finish very fast.
Thank you.
Okay, then we have these two latest ones, which are basically about the regenerating machines and then these cognitive systems. And then there's some interesting part is, for example, how the machines are becoming societally aware and how they also are kind of become some kind of legal entity. And then how the network should support that when these things happen, we, for example, have the right logs, we have the right tools to handle that kind of evolution. Then what I wanted to say is how this kind of match together with the network and the communication is that we actually extend this kind of stacks where we are in the network, in the communication part, to go further to what we call agent interaction. So how these devices will talk to each other. And then there are different levels in the stack that will be actually extended towards the actual model where we only end in an application level. Of course, we can take it also in that level, but then there will be sub-functions and like lifecycle management, orchestration, and policy handling that need to be taken in consideration for that kind of intelligence that the device has. And then on top of that, you will have the application. So actually, this stack is not that it's on top of the applications, but maybe something in between, still the application layer. Well, that's all my last slide. So please, if you have any questions, I'm happy to take it.
So we'll move the questions to the chat. For people who had, I would say, draft overviews, we'll have time for Dirk's. And Dirk, you can make it kind of fast. And Hemant, maybe you will just have time just to show one slide and just summarize really fast what you wanted to tell us. And like I said, I think you have to maybe reconfigure your drafts to make sure that they're looking at research and not IETF. So Dirk, if you can go really fast, if you're still on. Drawson?
Yeah, I'm
okay.
here. Sorry. Okay. So.
And Heyman, just make sure that you're standing by.
Okay, can you see my screen, hopefully? Sorry.
Yes, we hear you and we see it.
Yeah, good. Just maybe I was the only one noticing that, but Heyman's slides are actually not referenced in the agenda. It's 3 times the same slide, ours. That's listed there as a link, so you might want to change that. I'm happy about getting the airtime for our slide, but it's maybe overdoing it a bit. So just very quickly through the changes, we started also looking at ongoing efforts in relevant technology areas. That's probably what you meant about not looking towards the IETF, where I felt to an extent. That's the new section 6 that we did, but it may be quite interesting to add that. If that's not wanted, we can drop it again. What we did is the bigger changes, we moved the use cases into the use case draft that you co-edited as well, Marie Jose. That's just a stab that has the references in there, so it's shorter. The requirements, I've come to that, they have been linked clearer to the technologies in section 5. The section 5 has a mixture of both standardization efforts, but also research papers, and we want to expand that if possible. And then the section 6, as I said, is new. Requirements are put into 8 different ones. Now they have been slightly changed compared to before, because before they were more oriented towards the use cases which have been moved off. So now they are a little bit more related to the technology area. So there's a slightly different one. I won't be reading through them, so don't be worried about that. So their grouping changed because of that. So it's more technology oriented, not use case oriented. And we're also discussing of how to get some of those requirements straight into some of the use case discussions. And I said that that's the mapping of requirements and standardization efforts that was done. It's a very initial list, not claiming to be exhaustive. And maybe in order to accommodate your comment before, I'm very happy to extend that and scrap the standardization only and actually put that into a large referent list. The point was that we have something that maps from requirements onto links. Extending that to research links is obviously quite easily possible. So that would extend them beyond the standardization. So that's something we could do for the next revision. But that was the idea there, to look in the grouping of the requirements onto ones. As I said, the future plans are to fill in the missing subsection. We still haven't tackled the dynamic contracts. In particular, there is a lot going on in various efforts, both in research and in platforms, as you know. We also would like to more clearly, I know that I already said that last time, but I didn't really get to it, to link this to other coin drafts. We've done it with the use case draft. We also are getting slowly, I think there is some linkage now with the transport draft that I work with Ike on. So I think we're getting there, but there are other things that can be done in section 5. Update section 5 is more relevant efforts, and I said I'm happy to scratch the SDO focus only, and then obviously there are already research efforts in there, in all fairness. It's not only SDO. If anything, probably I wanted to add more SDO efforts in order to highlight what it actually is that standards haven't done so far yet, right? That's the idea. Same with the update as in section 6 that I mentioned before, which is that that list are the mapping of requirements onto ongoing efforts. So that's the one. And then you know, the question if you want to stick an RG draft on that, it's still running as a individual draft, which is fine with me, obviously.
Yeah, actually, this is something that we will not have time to discuss, but you were going to be discussed as becoming an RG draft, because this is well advanced. I will push that discussion to the list, but yes, I think this is a draft that should be adopted as a research group draft. So thank you very much for having been really fast. Hemant, sorry to have pushed you at the end here. Maybe you can just do first a short presentation of what you've been doing, and then just summarizing your 2 drafts into one, if possible. I hope you're still there. Is Hemant still there? Hemant is not there. Oh, then it's great. So we'll be able to finish on time. Maybe then I can share my screen. And obviously it does not working. Eve, could you reshare your screen?
Sure, let me just see where it is.
It will be just really, really fast.
Yes.
I will start talking while you're sharing. Obviously, we want to have an interim sometimes in May to review the milestones. We're lucky that we are in a very active and dynamic field where there is a lot of activity, and so the milestones are evolving, I think, as fast as we can. And also we will meet probably not in San Francisco, but at least virtually. Can you go back to future plans? Yes, and so we would like maybe to have a theme. Today you saw there was a lot of presentations that were not clearly related. They were all clearly related to COIN, but maybe we want to have a theme. So if somebody has ideas, please send it to us. You can go next, Eve. So we had actually one draft presented today, and we will like to push it to RG document. We already have one, which is the use case, and obviously Hemant could not stay as long as maybe he wanted, but those will be presented. We can present them at a later meeting. Next slide, Eve. So these are the other drafts, and actually I would like the authors of expired drafts to advise us on future intent. Actually, we would like the authors to advise us, especially the ones that were like the directions, which was very interesting, the security one, which was very interesting, and then there was a number of discovery drafts that also I think could come back into play. So it's not for now, but for all of these authors, you know who you are. So please advise us on what you want to do. Next slide. And that's the milestones. We have a ton of milestones that none of them is 2021. And I think we've achieved a lot of them. I don't want to discuss that again, but this is what we would like the interim to be doing. So we will probably not have a lot of presentations, maybe one, and then keep all the time, or one or two, and keep all the time to discuss that. And that's it. Now,
at the top of the hour.
Yeah, because Hemant didn't show up. So yeah, we're actually 20 minutes over time. But that's fine. Thank you so very much, everyone, to have spent the last 2 hours with us. Again, I think we're very lucky. We're in a very, very dynamic field. There's an awful lot of research happening, and we're very happy to offer a home for that research to be disseminated, and also to have a home for that research to be further defined and to find new ways of connecting computers and networks. Thank you so much.
Thank you. Thank you.
Thank you. Bye.
Thank you very much to the speakers and everyone who participated.
And the people asking questions. Thank you so much. Bye.
Marie-José, Jeffrey, does the tool itself capture all the chat, or do I have to copy it and paste it somewhere?
At the left.
Okay. Well, I will capture the notes in the chat window.
Maybe you can try.
Yeah, I got it.
And quite a few people are suggesting we have more discussion time.
Yes, including me. I say it every time.
Okay.
Okay.
Me too, yeah.
We can discuss offline, but thank you.
It's ridiculous. So 2 hours, 2 hours should be enough, right?
You got to schedule differently. Okay. Yeah. I'm going to sign off. Bye-bye.
Yeah. See you next time. Bye.